Alright, in this two-part lecture, we're going to try and understand the big O notation. Here's the definition, which is quite complicated. So we'll work towards this definition and kind of try and understand things intuitively as we work our way towards this definition. Now, just so you know, so we have an idea of what we're doing, it's all about comparison. Let's say that somebody suggests a place to go eat dinner tonight, and you say, well, how expensive is it? They might tell you, well, it's not as expensive as this place, but it's going to be more expensive than such and such a place. See, we do this all the time. We interpret new information by comparing it to information we already have. Now, with functions, sometimes we might be interested in how fast functions grow. For example, with algorithms, you might be interested to know how complicated an algorithm gets. How many steps does an algorithm make? Let's say that there's an algorithm that sorts 10 numbers. You follow certain steps to sort 10 numbers. You might be interested to know, well, how many steps will it need to make if I'm going to sort 100 numbers? What about 500? What about 1,000? See, so you're kind of interested in knowing how complicated an algorithm gets down the road. In order to have a sense of that, we need to be able to compare functions. Okay, so the big O notation is all about comparing functions. In particular, it's interested in how fast one function grows compared to another. So I want you to think of the tortoise and the hare. Okay, the hare moves quickly and the tortoise moves slowly. So we want to come up with a way to look at functions. Okay, two functions, and be able to call one the hare function and the other one the tortoise function. In other words, one function grows quickly and the other function grows not as quickly as the hare function. Okay? So that's what we're interested in, which function grows quicker. Now, how do we formalize this? What condition can we give to be able to assign one function, the hare function, the fast-growing function, and the other function, the slower-moving function? Well, you might say, why don't we say that the hare function will be the function that's greater than or equal to the tortoise function? Okay, if you have two functions and one of them is greater than or equal to the other function, we'll call that the hare function. Let's take a look at a picture. Here we have two functions. Now, which one of these moves quickly? Well, if you look at the picture, this one has a lot more pep in its step than this top function. If you look at our definition, though, according to our definition, this slow-moving top function is going to be the hare function because at every point it's greater than our tortoise function. See, we messed up. Our definition doesn't cut it. Looking at these functions, clearly this bottom function moves quicker. We want to call this our hare function, but according to the rules that we made up, that's not the case. Okay? So this doesn't cut it. Our first try was to say, okay, call the hare function the function that's greater than or equal to the other function. But this gets messed up if one function's pointing in the other direction. I don't really care about positive or negative. I just want to know which function grows quicker. So if I don't care about positive or negative, there's a quick fix to this. We introduce absolute values. Now, I'm not looking at any negative values. I don't care about negative. I'm only interested in magnitude. So let's take a look at the picture. Here are old functions from the first example. Okay, I called the bottom function f and the top function g. Notice what this looks like when we introduce absolute values. Now we're cooking. Now we're on the same page with both functions. You can clearly look at this example and say, okay, this function, this is going to be my hare function. It moves a lot quicker than the other function. Right? So this is what I'm going to call my hare function. So the absolute values help put things on the same page so that you can compare apples and apples. There's an issue, though. Notice that, give me a second here. Notice that, according to our definition, the hare function is just a blanket statement, has to be greater than or equal to the tortoise function. Look at all the values below 2, though. If you look to the left of this line, where 2 is, you'll notice that the blue function, which obviously grows quicker than the red function, this blue function is actually less than or equal to my slow function. But does that change things? Not really. If I'm interested in how fast a function grows, I'm just interested eventually. If there's a turning point down the road somewhere where one function is and remains forever greater than the other function, I don't really care what happens in the beginning. Okay, with algorithms, for example, I don't really care how many steps you take with small values. I'm thinking big picture, I'm thinking down the road. So really, what we mean is we want this to happen. We do want our hair function to be greater in magnitude than our tortoise function, but we mean eventually. We mean down the road. Now let's look at our picture. At 0, my hair function is actually less than or equal to. Alright, see, my blue function is less than the red function, less than or equal to the red function. At 1, my blue function is still less than or equal to my red function. But after 1, my blue function is in fact greater than or equal to in magnitude than the red function. Okay, so really what I want to say is ignore 0 and 2. Just start looking after 2. After 1, I mean. So formally, well, let's say after x equals 1, this inequality is true. In other words, for x greater than 1. So I'm saying ignore all this stuff and just start paying attention after 1. So start paying attention at 2. So this might feel like cheating, but it's not, because remember, when we're interested in growth, we're just interested in down the road. We don't care what happens initially. So because of that, I say, okay, ignore everything up to 2. So only start looking after x equals 1. Okay? So that's where that comes into play. Let's do a little recap. Oh, and also notice that if my blue function is greater than or equal to my red function after 1, so starting at 2, notice that it's going to be greater than or equal to after 2. After x equals 2. It's going to be greater than or equal to after 3. It's going to be greater than or equal to after 4. Anywhere over here, and after any of these x values, my blue function will always be greater than or equal to. Okay, so the definition of big O notation doesn't say find the smallest number where it starts to work. It just says after some number. Okay, so I could say after x equals, or for x greater than 1. I could have just as easily said for x greater than 2 or x greater than 3, x greater than 10. It doesn't really matter. You got to think big picture. Just as long as after some point, if you can say for certainty after this number, my hair function is going to be greater than and stay greater than my tortoise function, then we're in business, okay? So let's do a little recap. Big O notation. Our first try was, let's let the hair function be greater than the tortoise function. That failed, okay? It doesn't work. Because if you're pointing in opposite directions, you might end up calling your slow-moving function your hair function, and your tortoise function might grow a lot quicker. So that was a bomb. So we couldn't do that, so we said, okay, let's introduce absolute values. This was a lot better. The only thing that happened when we introduced absolute values is that there was those initial values that kind of threw us off, but we don't care what happens at the beginning. We just care that at some point and eventually, our hair function is greater than or equal to our tortoise function. So we had to formally say that. Well, really what we mean is the hair function should be greater than the tortoise function in magnitude eventually, after some point k, and mathematically we just said whenever x is greater than k. That's all that's saying. Whenever x is greater than k may look cryptic when you first look at the definition, but it's just saying at some starting point, in this case it happens to be k, at that starting point, after that, no problem, our hair function is always going to be greater than the tortoise function in magnitude. Okay, so we came up with some pretty good criteria to be able to concretely, rigorously define when one function grows quicker than the other function. Oh, that we were done, but we're not. There's one piece that we're missing. Let's go back to the definition of big O notation. We talked about why we have to introduce the absolute values. That's not that big a deal. We talked about why we have to introduce this k business. That just means that we're interested at eventually, after some point. What we haven't talked about is where this mysterious c comes from. Why do we throw this extra constant into the mix? Well, to answer that, you're going to have to watch part 2. Alright, in the first video, we talked about how when we're trying to describe what we mean by one function grows faster than another function. We talked about why we wanted to introduce absolute values. We talked about where this comes from, why we have to find some number k and say whenever x is greater than k. Basically, it just means eventually. What we didn't talk about is where this constant comes from. Why in the definition of big O notation they say they introduce this constant? Well, it turns out that if one function grows faster than the other function, it doesn't matter if you introduce constants or not, because the faster growing function will always catch up. Notice that in these functions, if we leave them as is, when does the fast growing function catch up and exceed g of x, the slower growing function? Well, it happens at 2. What if I decide to up the ante and multiply g of x by the number 2? What if I decide to double it? Well, it turns out that I delay the inevitable a little bit. So I have to look all the way down the road at, just a little past 3. But eventually f of x, my fast-moving function, still catches up. What if I multiply g of x by an even bigger number? Let's say 10. Well, I go off screen. But notice, f of x doesn't catch up until around 9, but it still catches up, okay? So the moral of the story is, if one function actually grows faster than the other function, it will always catch up at some point. Maybe that k point, okay, that threshold point is going to be different, but it's going to happen. So that's the moral of the story. You can multiply a function. Once you know that one function grows faster than the other, it doesn't matter if you introduce constant multiples. Okay, it might change the details of when things happen, but it doesn't change the fact of the situation, which is it will always catch up. Now you might be saying, okay, you can introduce a constant and it doesn't change anything. The question comes up, why would you want to introduce the constant? Doesn't that make things more complicated? Well, the constant actually simplifies things when you're trying to prove something. How does it simplify things? Well, there's something called the triangle inequality, and it says that in absolute values, absolute value of a plus b is going to be less than or equal to the absolute value of a plus the absolute value of b. Now, how does that help anything? Well, it lets you kill two birds with one stone, in a manner of speaking. Let's say you have two functions, f of x and g of x, and you know that both are big O h of x. What does that mean? Well, it means that you know that h of x grows faster than f of x. It means that you know that h of x grows faster than g of x, which formally means this. So after some point k1, after some number k1, the absolute value of h of x is always going to be greater than or equal to the absolute value of f of x with this little fudge factor. Okay, remember we can introduce constants, it doesn't matter. So this just follows from the definition of what it means for a function to be big O of another function. It means that it grows quicker. Basically these are saying that after some point, possibly two different points, my h of x is going to grow quicker than both f of x and g of x. So what I'm going to do now is I'm going to use this information to show that h of x is actually growing faster than f of x plus g of x, which isn't a gimme if you think about it. I know that h of x grows faster than f of x. I know that h of x grows faster than g of x. But how do I know that when I add f of x and g of x together, it doesn't become so strong that f of x plus g of x actually ends up growing faster than h of x? See, there is that question that we have to answer. But you can actually easily show that, in fact, when you add f of x and g of x together, it doesn't matter. They're not going to be stronger than h of x. They're not going to grow any faster. Okay, how do we show this? Well, first of all, so h of x with some fudge factor is bigger than f of x. H of x with some fudge factor is bigger than g of x. So I'm going to say, okay, I don't care, just pick the bigger number. Okay, remember what this number means. This means eventually. So for this to be true, you have to start looking after some number k1. For this to be true, you have to start looking after some number k2. I say, let k be the bigger of the two numbers, okay? I'm not going to mince words. Just pick the bigger one so that it works for both situations. So I'm going to let k be the bigger number of k1 and k2. So that means that whenever x is greater than k, I don't need to mess around with two different starting points or turning points. Whenever x is greater than k, I know that both of these things are happening. Again, what are these things saying? They're saying that h of x with some fudge factor, c1, is going to be greater than f of x. It's saying that h of x with some fudge factor, c2, is going to be greater than g of x at some point, okay, down the road after k, after the number k. So if I know that h of x with these fudge factors is bigger than f of x and g of x individually, how do I know that it's going to be bigger than both of them combined? Well, that's where I use the triangle inequality. What does the triangle inequality say? Oh, again, it just says, by way of review, that I can break up a sum in absolute values. So if I have the absolute value of a plus b, that's going to be less than or equal to the absolute value of a plus the absolute value of b. So if I'm looking at the absolute value of f plus g, I know that this is going to be less than or equal to the absolute value of f plus the absolute value of g. And remember, I already have a bound for absolute value of f of x. I already have a bound for absolute value of g of x. Remember, that's what we were talking about. That's what we're assuming from the very get-go, is that h of x is going to be bigger than these functions, with some fudge factor. Now, I have c1 of these here plus c2 of these here. That means I'm going to have c1 plus c2 of them. Actually, let me explain that a little different. It's real easy. If you have 4 apples and somebody gives you 3 apples, you have 7 apples, right? So you have this many of something plus this many of something, so you just add them up to get the total. If you have 3 oranges and somebody gives you 2 oranges, now you have 5 oranges total. Okay, so that's what happens here. I know that the absolute value of f of x plus g of x is going to be less than or equal to this. c1 plus c2 of h of x. Basically, I have to add my 2 original fudge factors together to get my new fudge factor. So I'm simply going to define, instead of writing c1 plus c2, I'm just going to define c to be c1 plus c2. So going back to my illustration, if you have 5 apples plus 6 apples is 11 apples, I'm not going to say 5 plus 6, I'm just going to say 11. Okay, so that's what I'm doing here. I'm defining c to be the sum of the 2 original fudge factors. And notice what I have. I have that in absolute values, f plus g is going to be less than or equal to this fudge factor times h of x. Again, after some point k. And where does k come from? It comes from my original eventualities. I knew that h of x is going to be bigger than f of x at some point. It's going to be greater than g of x at some point. I said, okay, just pick the bigger point of the two. I don't care. I'm not interested in finding the smallest one. I just want one that works. Okay, so whenever x is greater than k, of course. Okay, so why is this helpful? Well, think about it. When you look at a math problem, usually is it just one thing, or is it a bunch of things added and subtracted from one another? It's usually some different terms added and subtracted from one another, right? So what that little fudge factor c lets you do is it lets you use the triangle inequality to break everything up into pieces, and then you just have to worry about putting a bound on the pieces. Okay, and it doesn't matter if you end up having to add up all these other things together, because it doesn't matter, because we allow there to be constants in the definition of big O notation. So if you want to look at example 1 on page 206 of the text, and I'm talking about the 7th edition of Rosen's discrete math textbook, you'll see how this happens. So one more time. What is the definition of big O notation? Well, it means that one function is a hare function and one function is a tortoise function if there exists 2 numbers. One is c, which is our fudge factor, and one is k, which is our turning point, such that in absolute value the tortoise function is always less than or equal to some fudge factor times the absolute value of the hare function. And this fudge factor ends up becoming important when you're looking at a bunch of terms added together and you just want to start bounding, that function piece by piece. Okay, we've talked at length of what it means for one function to be big O of another function. We talked about what it means for f of x to be big O of g of x. How do we actually show or establish this relationship with two functions? Well, let's look at an example. Show that 15x cubed plus 7x squared plus x. To do this is, well, generically, let's talk about how we establish this relationship. How do we show that some function f of x is big O of g of x? In other words, how do we establish that f of x grows more slowly than g of x? Well, to show that f of x is big O of g of x, I need to find constant c and k. So all the work is in finding constant c and k such that whenever x is greater than k, so k is like my turning point, in absolute values f of x is less than or equal to the multiple c of, in absolute values, g of x. And this c is like my fudge factor, which will make more sense after we get done with this example. So I need to find these two numbers. I need to find my fudge factor c, and I need to find my turning point k, where this relationship always exists. So this is generically what I need to do. Let's throw our actual functions in from our example. So for this particular problem, I need to find a constant c and k such that whenever x is greater than k, in absolute values, 15x cubed plus 7x squared plus x plus 17 is less than or equal to the multiple c of, in absolute values, x cubed. This is what I need to find. I need to find c and k so that this is always true whenever x is greater than k. I can simplify this a little bit. Notice that I can get rid of the absolute values because there's no subtraction. So as long as x is always positive, there's no way that I'm going to have negatives anywhere. So if I don't have negatives anywhere, I don't need to worry about absolute values. So let me do that. Let me say that x is greater than 0. That way I can get rid of the absolute values. Now you might feel like this is cheating, but it's not. Remember, I want to find a value k, and I'm going to say that whenever x is greater than this number, that's where you need to look. So I can start off by saying, right off the bat, make x greater than 0, so I can ditch the absolute values. You can always, always, always say, make x bigger than some number when you're trying to establish the big O relationship. Okay, so I've gotten rid of the absolute values by saying x is greater than 0, limiting my attention there. Now, how am I going to find some magic number c, some magic multiple of x cubed, so that I know for sure that this will always be less than or equal to that multiple of x cubed? Well, what we're going to do, and this is common, is you divide and conquer. Notice that my polynomial has 4 terms, right? Oh, I didn't need to do that yet. I have 15x cubed, I have 7x squared, I have x, and I have 17. What I'm going to do is I'm going to show that 15x cubed, this single term by itself, is less than or equal to some multiple of x cubed. Then I'm going to show that 7x squared, this term by itself, is less than or equal to some multiple of x cubed. Then I'm going to show that x, this term by itself, is less than or equal to some multiple of x cubed. And then I'm going to show that 17 by itself is less than or equal to some multiple of x cubed. Once I've bound each piece individually, then I can put it all together. Okay, so step 1, show that 15x cubed is less than or equal to some multiple of x cubed. So really I'm asking this question. Is it true that 15x cubed is less than or equal to some multiple of x cubed? Obviously the answer is yes. Just let c equal 15. 15x cubed is less than or equal to 15x cubed. No problem. This was almost a gimme. Let's move on to the next term. How do I go about showing that 7x squared is bounded by or less than or equal to some multiple of x cubed? Well, x squared is less than x cubed, right? So I can just say that because x squared is less than x cubed, then 7x squared is going to be less than or equal to x cubed, right? Well, kind of. We need to be careful, and this is why. If you have a number, a fraction, if you have a number between 0 and 1, cubing it is actually going to make that smaller than squaring it. And this is an example. Notice that 0.5 squared is 0.25, but 0.5 cubed is 0.125. So by cubing a fraction, it actually gets smaller than if you square it. So I can't say just blindly that x squared is less than or equal to x cubed, because x cubed will be smaller than x squared if you have a fraction. No problem, I can take care of this though. Let's just focus on numbers bigger than 1. See, if I look at numbers bigger than 1, then yeah, when you cube it, it's just going to get bigger than when you square it. So I can say that x squared is less than or equal to x cubed as long as x is greater than 1. Okay? Now, you might be tempted to say, well, why x greater than 1? Why not x greater than or equal to 1? Well, look at the definition of big O notation. I don't care about less than or equal to. I just care about finding, or just look at the notation. The notation says x greater than k. So yes, technically, this relationship is true as long as x is greater than or equal to 1, but I don't care. I'm just going to say x greater than 1. Okay, when x is greater than 1, x squared will always be less than or equal to x cubed. X cubed will be bigger. You're multiplying it by a number bigger than 1, so it's going to be bigger. So again, let's return to this. I want to say that 7x squared is less than or equal to 7x cubed, right? Then I'm done. I've bounded 7x squared by a multiple of x cubed. And I can do that as long as I say that x is greater than 1. Moving on. Is x less than or equal to some multiple of x cubed? I'm moving on to the next term in my function here. Is x greater than or equal to some multiple of x cubed? Well, yes, of course. X is going to be less than or equal to x cubed. Again, under this caveat, whenever x is greater than 1. So if you take a number greater than 1 and you cube it, that's going to be bigger. Okay, so I've managed to bound this term by a multiple of x cubed, namely 1x cubed. Moving on to the last term. Can I make 17 less than or equal to some multiple of x cubed? Yes. There's lots of different, actually, let me just address something first. You might be tempted to say, well, I want to find exactly when x cubed becomes 17. So I want to say that x cubed is a cube root of 17, and then if you cube it, I'm going to stop myself there. You don't need to go down that path and find the exact point when x cubed hits 17. You can just be lazy about it. You just know that x cubed is greater than 1 whenever x is greater than 1. So how do I make 17 bounded by some multiple of x cubed? I just go ahead and write 17x cubed and make sure that I say whenever x is greater than 1, so that you're multiplying 17 by a number greater than 1. This might seem sloppy, but it's okay. It doesn't matter. All I'm interested in is finding some multiple that I can put in front of x cubed to ensure that 17 cubed. This works. So all I need is something that works. Okay, so individually, I've bounded each term of my function, right? I know I said that 15x cubed is less than or equal to 15x cubed. I said that 17x squared is less than or equal to 17x squared, again, whenever x is greater than 1. So I can replace each term by the bigger term. So I replace 15x cubed by 15x cubed. I replace 7x squared by 7x cubed. I replace x by x cubed. I replace 17 by 17x cubed. And this inequality holds. And notice, I can just simplify the right-hand side now. 15x cubed plus 7x cubed plus 1x cubed plus 17x cubed simplifies to 40x cubed. I'm done. I have shown that 15x cubed plus 7x squared plus x plus 17 is big O of x cubed, where c equals 40 and k equals 1. Now, in my next example, what if I had something that had negatives in it? Notice here, it kind of felt like cheating. I managed to get rid of the absolute values because there were no negatives. What if I have a negative here or a negative here? Then I kind of have to, I can't just get rid of the absolute value so willy-nilly. So what I'm going to do in my next example is look at a very similar problem, except this one's going to have minus signs inside of it. Okay, so this is part 4 of the video lecture series on big O notation. Do not go through this unless you've gone through part 3 first. Otherwise, part 4 isn't going to make sense. Now, if you remember at the end of part 3, I left you with a question. It felt kind of like cheating because I used a very specific example or a very specific function in part 3 of the video series that had all addition. And that helped me get rid of the absolute values. But what if I have negatives? I can't just ignore my negatives. I can't just throw out the absolute values. So I have to do something a little different. And what I'm going to show you, and why it's so important to watch part 3 of the video series before part 4, is I'm going to show you that this problem actually becomes the exact same problem as in part 3 of the video series where I had all plus signs. Okay, let's get there. So again, just as a reminder, how do I establish that one function grows no faster than another function? In other words, how do I show that one function is big O of another function? Well, to show that f of x is big O of g of x, I need to find constants c and k such that whenever x is greater than k, in absolute values f of x is less than or equal to c times the absolute values of g of x. My fudge factor. So let me actually throw my particular functions into this template. So what I need to do is find constant c and k such that whenever x is greater than k, in absolute values 15x cubed minus 7x squared minus x plus 17 is less than or equal to c times an absolute values x cubed. Now before, in part 3 of the video series, I had plus signs here, so I can just make x greater than 0 and I could ignore the absolute values because I'm never negative, so I never have to worry about absolute values. However, that's not true here. I can't guarantee that just by making x greater than 0 that this whole thing together is going to be positive. So I can't ignore my absolute values. What I'm going to do, and what you do in general, is use the triangle inequality. Remember in part 2 of the video series I made a big stink about the triangle inequality? Just a reminder, this is what triangle inequality says. And this is just a mathematical truth. Whenever you're taking the absolute value of a sum, so a plus b, I'm taking the absolute value of that, that's going to be less than or equal to the sum of the absolute values. Basically, it's saying if you split up an absolute value, you can only get bigger. You'll never get smaller. You might be thinking, well, I don't know how that helps when I have negatives. Well, there's nothing in the absolute value, in the triangle inequality that says that a or b is necessarily positive. So let me reformulate it this way. The absolute value tells me that if I have negative a plus negative b in absolute values, this is going to be less than or equal to, in absolute values, negative a plus negative b, which, since I have absolute values on these, the negatives disappear. And there you have it. Notice that the triangle inequality has let me get rid of the negatives. There's a price you pay, though. Instead of having an absolute value of a sum, you have to have a bunch of absolute values on each piece. Okay? So that's what I'm going to do here. Let's return to this. I'm trying to show that in absolute values, 15x cubed minus 7x squared minus x plus 17 in absolute values is less than or equal to c times the absolute value of x cubed. Of course, whenever x is greater than some number k. I use my triangle inequality on this piece. I'm going to split it up. The triangle inequality tells me that this is less than or equal to the absolute value of 15x cubed plus the absolute value of 7x squared plus the absolute value of negative x plus the absolute value of 17. See, that's what the triangle inequality lets me do. I know that this is less than or equal to this. And now, since I have absolute values, these negatives disappear because that's what absolute value does. It makes negatives disappear inside. So I have a single term in here. I can get rid of the negative in here and the negative in here, again, because I have absolute values. So now what I'm going to do, see, I was trying to show that this is less than or equal to c times x cubed. Now I'm going to show that this is less than or equal to c absolute value of x cubed. And that's fine because I know the triangle inequality tells me that this is less than or equal to this. So if this is less than or equal to this, and this is less than or equal to this, then you have it. You have that this is less than or equal to this. Okay. So now I want to find constants c and k such that this is less than or equal to this. Be done. But notice, on the left-hand side, because of the triangle inequality, I got rid of all the negatives, right? Now I can just say, well, look at x greater than 0. If x is greater than 0, nothing is ever going to be negative, which means that I can ignore or I can toss the absolute values because nothing is ever negative. Notice that this is exactly the same thing I was trying to prove in part 3 of the video series. So even when you have negative signs, you can get rid of them using the triangle inequality. So I'm not going to go through the whole hoopla right now, but let's put it all together. Yes, this is exactly what I did in part 3 of the video series. Let's put it all together. I'm trying to show that 15x cubed minus 7x squared minus x plus 17 is big O of x cubed. So that means I'm trying to find constants c and k such that whenever x is greater than k, in absolute values, 15x cubed minus 7x squared minus x plus 17 is less than or equal to c times an absolute values x cubed. This is what I'm trying to show. I'm trying to find numbers c and k so that this is always true. So what did we do? Well, we started off with showing that this is less than or equal to this by the triangle inequality. Now we simplified this right-hand part a little bit to this. Then what did we do? Well, we just got rid of the absolute values again by saying x is greater than 0. If x is greater than 0, then nothing is ever negative and the absolute values are redundant. Now, what did we do from here? Well, from here, this is what we did in part 3 of the video series. Not what I did earlier in this video, but what I did in part 3 of the video series. In part 3 of the video series, I just said, okay, I'm going to bound each piece individually. So I did that. 15x cubed is less than or equal to 15x cubed. 7x squared is less than or equal to 7x cubed, again, whenever x is greater than 1. Similarly, x is greater than x cubed whenever x is greater than 1. And 17 is less than or equal to 17x cubed whenever x is greater than 1. Okay? And this right-hand side simplifies 15 plus 7 plus 1 plus 17 is 40. So there you go. I've established it. I've established that 15x cubed minus 7x squared minus x plus 17 is big O of x cubed with c equal to 40, okay, and k equal to 1. This, in general, is how you show, especially if you have a polynomial, how you establish the big O relationship.